Hello everyone, in this data analysis tutorial I am going to talk about genotype by environment interactions by doing stability analysis, which is usually studied by conducting a multi-environmental trial. Then we will fit different models like AMMI and estimate some of the stability parameters and also create biplots to study the interactions in general. And in this tutorial I am going to show you the most of the data analysis part with fixed effect models, and the important topics which I am going to cover are stability analysis, fitting an AMMI model, and getting different type of GGE biplots. So before getting into the analysis part, let me clear one of the important concept which explains why we need to do the multi-environmental trials and what is the logic behind it. Here I am considering an illustration regarding plant height in linseed or flax whatsoever depending upon your region. In this crop, plant height is one of the most important trait when we are considering it for fiber purpose. In this image, we can see the technical stem length. The first two having long and slender stems with flowering confined to the uppermost part are most desirable when compared to the dwarf plants. Keeping these things in the mind, imagine we are considering two different genotypes growing in two different environments. One is hotter and another one is colder. If the performance of the genotypes, in this case height of the plants across the environment, is same, then we can consider them as stable interactions. But this is not the ideal case, so let's get into the most often interactions. In this scenario, as you can see, the height of the both genotypes A and B is better in the cold climate when compared to hotter one, in a way that the benefits are added across the environments. If A grows 10 cm tall in the second environment, then B also grows approximately 10 cm tall. So these kind of interactions are called additive interactions. In the next case, the performance in terms of height of the genotype C has increased in the second environment and the height of the genotype D has decreased, and these kind of interactions are called diverging interactions. And in the case if the benefits not adds up equally across the environments, then those kind of interactions are also called as diverging interactions. Then in the contrasting case, here the performance of the genotype E gets slightly lower in the second environment, while the performance of the genotype F gets closer to the performance of genotype E in the second environment. These kind of interactions are called converging interactions. And in the final case, the performance of the genotype G gets lower in the second environment, while the performance of the genotype H overtakes the performance of genotype G in the second environment. And these type of interactions are called crossover interactions. And these are important for the breeders because if we have not performed multi-environmental trial in these environments, then we would recommend the genotype G instead of H. Then it wouldn't be better for the farmers. So that is the reason of these trials, and we study these interactions by calculating different stability parameters with the help of statistical modeling, and this is the ideology behind. And if you are interested in them, I recommend studying these research papers. There are two research papers we need to study, and the first one is this. The author of this paper is Molo Setti and co-workers. So in this research paper, we will find 16 different statistical equations modeling different interactions, and also you will find these basic interactions what I told previously in this video, and this is purely based on statistics. So if you are interested, you can study. In case if you want to understand about the concept of mixed modeling, I recommend studying this review paper, Methods for Comparing the Yield Stability of Cropping System by H. P. Fu. This is basically an agronomy related research paper. Here E is considered different cropping systems, while in case of plant breeding we study the stability of different genotypes. That's the only catch here. In agronomy we can use different treatments such as fertilizer trials, cropping systems, sowing dates, etc. for the stability analysis itself. And these two research papers or review papers are not must if you don't have any time, if you are hurry in your research works, so you can skip this. In this tutorial I am going to use a package called metan, and he is the author of this package, and we need to give a lot of credit for him because each and every function in this package has lot of importance. If you are new to my channel, you can see that the previous video which I made on correlation has only two functions of this package, and what you are seeing in this frame is known as cheat sheet. Here you can find all the functions which we can use in our analysis. With that said, If you ask me why we need to use metan only, because this is a complete package to do multi-environmental traits. If you consider other packages such as stability, you will find only functions which can do stability analysis, and AMMI stability also do AMMI based stability parameters, and GGE and GGE biplots can use it to produce GGE biplots. Agricola and plant breeding will help in parametric and non-parametric stability analysis. And there is no such a kind of interaction between these plots, as when compared to the metan, we can find the work is very much streamlined. We can use only one package to do entire multi-environmental trial analysis. And the most impressive part of this package is the sheer number of functions which are present for data cleaning and manipulation. Before getting into the data analysis, let me show what are the essentials we need to know for our analysis and interpretation of results. From the browser, if we key in metan in R and search, we will find a GitHub page here, and we need to get into that page in order to get the most updated information. Here you can find the topics here. So these are some examples. This is the cheat sheet what I have showed, and we can use this information as an example as the data sets are directly built in this package. So explore this, take your own time, and if you go to the Google search page, here we will find a research paper from the author itself. So if we get into that research paper published by British Ecological Society, in the bottom of the page we will find this information. From here we can cite the literature, and from the supporting information we will find a supplementary material which we can consider as a manual. So here we won't find updated information regarding the functions what we need to use in R, but the theoretical part in the manual is very much helpful for us. And the flow, here we can find from where to start and where to end. So this is a kind of must for you if you need to do the data analysis. You can download, you can save, or take a print of it and keep it with you. Here the only change what I see is there is no need to mention the replications in some of the functions like this GEFX. That is the only disadvantage with this manual, but I will address these issues in the analysis part. So let's get into the next research paper what we need to do. So from the Google, if we search for biplots by Ann and Tinker, from the search page we will find this title, biplot analysis of multi-environmental trial in the Canadian journal. So the website is nrcresearchpress.com. So if we get into that, we will get a research paper, and this research paper is must if you want to interpret the biplots. Here in this research paper, each and everything is addressed very well. So if you read this research paper once, you can interpret your biplots on your own. So take your time, read this research paper. It will be helpful for in your interpretation of biplots. So with that said, let's get into the R Studio and begin our analysis. The most important step before analyzing any data is its structure. Here I have stored my data in a folder name called MMET. MMET stands for Maize Multi-Environmental Trails, since the dataset which I am going to use is of maize crop. So this is how I have taken my data. The sequence goes like this. First, I have grouped my genotypes based on same environment. Then they are grouped on same genotypes, last by their replication, that is R1 and R2, as you can see that in a picture-in-picture mode on the Excel sheet. In case of alpha lattice design, we need to consider an extra column where the blocks are mentioned, and we need to pass this block argument while calculating ANOVA, including both joint and individual ANOVA. That I will talk in data analysis part. Since R is case sensitive, we should not mess up with the uppercase and lowercase letters. We should either consider uppercase or lowercase. Here you can see I have considered all the characters in uppercase only, either environments or genotypes. Here I have used E1, E2, E3 for environments and G1, G2 series for genotypes. Here we need to mention E and G separately, because in biplots, in order to get a distinction between environments and genotypes, if you only consider numbers, then we can't distinguish between environments and genotypes. There will be only one or two numbers. So keep this in mind and never mess up with small letters and big letters. If you consider uppercase E1 and lowercase e1, then R will detect them as two different environments or factors. So don't mess up with the first place. Keep them clean. Here in my dataset, you can see there are three different environments, that is E1, E2 and E3, and there are 12 different genotypes starting from G1 up to G12, and I have considered two replications, R1 and R2. Here the variables are height and yield of the maize crop. So here I have taken these headings in uppercase only, since by doing this you can be able to distinguish where I am keying in. So save the dataset before importing into the R. In case any data is missing, try replacing it with the mean values so that there will be no big effect on the data analysis. So I will save the data and close the Excel sheet in order to get into the R Studio. In the beginning itself, I would like to give some tips for the beginners. And the most important thing is not to skip the video for the first time. Since I am using only one package, the script is continuous and runs down up to last part of the video. So with a lot of patience, watch the video. At the end of this video, I will guarantee you will be capable enough to do your data analysis on your own. And here in the R Studio, we will describe a function to do a particular analysis with a set of arguments, and after each and every argument we need to separate them by comma. Then we need to execute that line of code by pressing Ctrl Enter or Command plus Enter based on your operating system. And R is case sensitive, don't confuse with the cases. And here we need to specify a function with particular case only, and increase the resolution of the video if the text is not visible for you. With that, let's get into the coding. So let me start the coding from a new R script. You can get that from here. So from here, we will start to write the code. Whatever I write after typing as is a comment. Here, the package which I am going to use is metan. This refers as an heading for you. In order to get that package, we need to use install.packages command. Within the parentheses, we need to mention the package name, that is metan, all in small cases. After that, we need to press Ctrl plus Enter in order to execute that line. After that, the package will start to download automatically and it will install later. Let me show you another way of installing the package from here. If we type the name of the package, if it is available in the CRAN repository, it will automatically show up here. Then we need to select and click on install, but I will cancel it out since I am installing by the command. Then after installing the package, as you can see here, the package has been successfully installed here. In the console we can see that. Then in the next step, we need to load the package. In order to load, we need to use library command. Here there is no need of mentioning the package name within double inverted commas within the parentheses. If we load the package using library function, then in the console we can see that the package has been successfully loaded up. Here we can find the version of the package, name of the author, etc. If we want to customize the plots, then we need another package known as ggplot2. In order to get that, use the same function install.packages. Within parentheses, we need to mention the name of the package, that is ggplot2 in double inverted commas. I will skip this line and directly load this package as I already have that in my R Studio. Next, in order to increase the maximum lines which are printed in the console, I will change the options by using this function. Options, within the parentheses, we need to type max.print and we need to select it to maximum extent possible. Here I will select 10,000 lines to be printed in the console. The next important step is to set the working directory. Here I will select the original folder which is there on desktop where our dataset has been stored, that is MMET. Then in order to cross verify the working directory, I will use getWD function in order to know the working directory. So getWD within parentheses, don't write anything, execute this line. Then in the console, as you can see, our working directory is indeed the MMET folder on desktop. The next thing is to import the dataset into the environment. In order to do that, click on Import Dataset and select from Excel. If you are using the RStudio for first time, then you wouldn't get this graphical user interface directly. In order to get that, we need to give certain permissions. So give all permission, then this interface appears. If I click on Browse, then I will get straightly into the working directory because I have already set the working directory, right? Then we need to select our dataset, that is MMET. So if you double click here, the dataset will appear here. This is only preview. We can't see entire dataset from here, but we need to confirm that the variables, that is height or yield, has to be there in doubles, which means numbers. If you want to change the dataset name, you can change from here, and if you want to change the sheet, you can change from here. By default, it will be first sheet only. And this is what the code which runs behind this graphical interface. I will just copy it and I will import this dataset. I will click on import. So once the table get imported successfully, we can view this here. So you can cross verify whether all the genotypes and the variables are there in the table. I will get back into the script and I will paste the code which I have copied from the graphical interface here. And if you execute these lines of code, it will be same as what we did by graphics. So we'll get into the same part. The reason behind why I did copy the text here is because if we change the data in the data frame, and once again we need to execute all the functions which we will do later in this tutorial, then there will be no need for to use the graphical user interface. We can get it directly at the end by pressing Ctrl Shift Enter. In order to do that, we need to save the script. So hit Ctrl S, then we will get into this interface. Here we need to type the name of the script page, then click on save. It will be saved. So you can see the name from untitled has been changed to script, and the color of the text is also changed to black. After this, if you want to know much more about our data, if we check the class of our data, simply by typing class within parentheses, we need to give our dataset name, that is MMET. If we execute that line, here you can see in the console, it only shows that it is a data frame or table. In order to get much more insights on our data, we need to check its structure. In order to do that, type str within parentheses, mention the data frame name, that is MMET. Execute this line. Here you can see that the environment, genotypes and replications are there in character. We need to convert them into factors. That is the most important step in data manipulation. So in order to convert that, we need not to just convert them as factors. We need to convert them as factors with the levels set to unique. Because if you won't convert them into factors with levels, while plotting the graphs, you will end up with the problem that I will explain with the graph further in this video tutorial only. In order to convert them as factors, let me select the column from the data frame. In order to select, we need to press $symbol, Shift 4. Here we need to select environment, and this specifies the place where we need to store our factors. Use factor function. Within the parenthesis, we need to select our column once again. That is, so from the data frame MMET, select the environment column. Additionally, we need to pass on extra argument known as levels. Then we need to set them as unique. So after unique, within the parenthesis, once again, select the column, that is environment, from the dataset MMET and execute this line. In the same way, we need to select the genotypes also. So the dataset name MMET and type $symbol, then select genotypes. Use the same function factor, then select the column from the dataset MMET, then also set the levels to unique. Within the parenthesis after unique, we need to select once again the genotype column, then we need to execute this line also. And the same treatment we need to give for replications also. In case if you are using alpha lattice design, then also you should convert your blocks into factors with level set to unique. Now, after converting them into factors with unique levels, if we check the structure of the data frame by using str function within parentheses, same, we need to give our dataset name. Here you can see the environment, genotypes and replications have been converted into factors with 3 levels, 12 levels and 2 levels you can see. So if we have not considered levels as unique, you won't find the sequence what you find here. Instead of G1, G2, G3 here in genotypes, you will find G1, G11, G12, G13 like that. In order to avoid that, I have converted the factors with unique levels. With that said, let me get into the next part, and it is most important part in this data manipulation, where we will check for the presence of outliers, missing values or not applicable values, and is there any messy text or text in numbers like that. And the function which I am going to use here is known as inspect. Within the parenthesis, we need to mention our data frame name, that is MMET. After that, with an additional argument known as plots, we need to set that for true in order to get the graphs, because graphs will help us a lot in visualizing our data. Here it will check for 3 columns, that is environment, genotypes, replication, whether they are present or not in order to do the data analysis. And it will also check the variables with the numbers in order to find the distribution and detect the outliers in them. Here you can see there are possible outliers in the variable height, and the next step is detecting the outliers in a variable. So let's do that. In order to find where the outliers are there, use find underscore outliers function. Within parentheses, mention the data frame name, that is MMET. Next, we need to specify where to look for the outliers. Here, for variable, I will select HT. HT is a short form for height, what I have specified in my data frame. Next, I will select an additional argument, plots is equals to true, and this will be very much useful for getting an histogram and box plot. If we execute this line of code, we will get some of the information like mean with the outliers, mean without the outliers. It will be useful very much in judging the outliers. Here you can see the mean without outliers is 146 and the mean with outliers is 152. As you can see, this is not a big difference, and the outliers which are there in this box plot are not very much far from the upper whisker. They are very much adjacent to the upper whisker only. And in the histogram, as you can see, the bell curve, what we can expect from normal distribution, is not too much skewed either left side or right side, which means either positively skewed or negatively skewed, as you can see that in a picture above the graph in the video itself. So in the lines, as you can see, it is the index of outlier. As you can see, they are adjacent to each other, 1112 and 5960. It indicates that these are from a same entry of 2 different replications. Here you can see that is the G6 in the first environment in both R1 and R2, and the same G6 in the third environment have high values. So we can't consider them as outliers because that is the actual performance of that genotype. If you consider the mean with outliers, that is 152 centimeter, we can find that there are so many genotypes around height of 150 centimeters, and this indicates that this is not an outlier which has to be removed. With this justification, I will keep these outliers in my data analysis. With that, let me show how we will get a box plot and histogram if we don't have any outliers. In order to check that, I will go back into the script and start detecting outliers in yield. In order to do that, use same function, that is find underscore outliers. Within parentheses, mention the data frame name, that is MMET, Maze Multi-Environmental Trials, and this time for variable, select yield instead of height, and the plots will remain here too. So if we execute this line, here you can find in the console that there are no outliers. Then it is good to go for the data analysis. So with that said, I will use some of the extra functions which don't have any real effect on my data, but it might be useful for you in handling any mess in the dataset. The first thing which I'm going to show you is how to remove the rows where there is no data or the rows with missing data. In order to do that, use remove underscore rows underscore NA. Within parentheses, we should mention the data frame name, that is MMET, in order to take out all the rows with empty values. If we execute that line in the console, you can see rows with not applicable values have been removed. With this function, there is no effect on my dataset. As I earlier said, there is no any missing values in my dataset. You can see here the total number of rows is same. So let me go back to the script. Now I will show you how to handle the zeros. In order to replace the zero, use replace underscore zero function. Within the parentheses, just mention the data frame name, that is MMET. If we execute this line, then the zeros will be replaced. While entering the data, we might do a mistake by misinterpreting the data. Instead of using 0, we might use O. In that case, we can find the text present in a variable, suppose in plant height or in plant yield. In order to find that, use find text in number function. Within parentheses, mention the dataset name and the variable where we need to find the text and execute this line in order to find the text. Here you can see integer 0. That means there are no text in my variables. In the same way, we can also find the text present in the second variable yield. For that, use same function find text in number. Within parentheses, mention the data frame name and in that select the variable that is yield. And if we execute the line, then also we will get similar results as we got in terms of height. Up to here, what I said is only the data manipulation and data cleaning. From now onwards, the real data analysis begins. That means the calculation part starts from here. So let me start with the descriptive statistics at the first. Let me borrow some space for you so that it will be clear for you to visible from the screen. In order to get the main statistics, you can use this function. Within that, we just need to mention our data frame name, that is MMET. If we execute this line, we will get the important statistics in the console. In order to get all the descriptive statistics of our data frame, we just need to pass an additional argument for the same function, which is stats is equals to all. All should be mentioned within double inverted commas. If we execute this line here in the console, you can see there are 20 more variables, but we can't see here in this console. In order to view them, let me store the stats in a new object called ds. We can copy the above function, but I will type the same function once again. When we execute this line, the output will be saved in ds. You can see the same has been saved in ds. In order to see the table, we have to use view function. Here, view has capital V. Whenever I will type view, it will be capital V only. So within view, if we give our object name, that is ds, and execute, then we will get a new table in a new page beside the R script. From here we can view all the variables stored in that object, and this we will keep on doing many times. For the first time, let me show you how to import this table into Excel format. Before importing, we need to cross confirm whether the object is a table or not. In order to do that, use class function. Within that, mention the object name. If we execute that line, you can see in the console that it is a table or data frame, so it is ready to export. From here onwards, watch very carefully because I am not going to import each and every table into the Excel sheet. I will do for this once, and later you can follow the same procedure for other tables also. In order to import a dataset, we need to have a package known as write Excel. So use install.packages command to install the package, and within parentheses mention write Excel within double inverted commas. Since I already have this package, I just ignore it. So the next step is to bring this package into the environment. So use library function. Within the parentheses, mention the package name, that is write Excel, and execute this line to get the package into the environment. The function which I am going to use to get the dataset is write underscore Excel sx. So underscore will be there between two words in every function. So if I keep on telling, it will be awkward, so I just ignore it. Within the parentheses, after mentioning the function, we need to specify the object where our table has been located, or the command which directs to the table. After that, we need to mention the name which we need to give for the table. So within parentheses, I will mention ds.xlsx. Here, .xlsx is the secondary name of Excel sheet or format name. After this, if we execute this line, then the table will be stored in the working directory. So if I go to the working directory, you can see that the table has been here. So let me open the table and show you how it looks. So this is the table, guys. Here you can see all the descriptive statistics present in Excel sheet. Just I will close it and I will go back to the R and start the coding again. The next step we need to do is calculating the mean performance in different combination. First, I will show you the mean performance of genotypes. I will store my values in an object known as mg, which indeed refers to mean of genotypes itself. The function which I am going to use here is means by, and within the parentheses we need to justify our data frame name, that is MMET. Since we want the means of genotypes, I will justify the genotypes as GEN. If you don't know what it is, this is the table heading or the column heading of the genotypes in our data frame. So we need to justify environment, replications, height and yield, so on from here. So keep that in mind. These are the short forms which we have taken in our data frame. If we execute this line, then the output will be stored in mg. So we can view this by clicking mg and executing this. Since I do have only 12 genotypes, it's appearing in console. If you have more than 12 genotypes, then it won't appear that much easily. So in order to view them, we need to use view function, that is capital V. Within that function, if we mention our object name mg and execute, we can find the table in a new tab in the RStudio itself. With that, let's calculate the mean of environments. I will store my values in an object known as mean, mean of environments. And the function which I am going to use is means by. Within the parentheses, we need to mention our data frame name. After that, I will mention the environment. If we execute this line, the output will be stored in ME. Then in order to view that, execute ME. And we can use view function if there are more environments which are not appearing in the console. In the next part, I will show you how to calculate mean performance of genotypes across different environments. And this will be very much useful in preparing our two-way table. I will store my output in an object known as MGE. And the first thing we need to do is to select our data frame, that is MMET. Then we have to pipe it through. If there are any newbies and don't know how to use the symbol, it's just percentage. After that we need to mention greater than sign. Once again we have to mention percentage. This is the symbol of a pipeline. Once after moving our dataset into the pipeline, we need to group them by our environments and genotypes. So within parentheses mention environment and genotype. Once again pipe it through. In the next step, we need to use descriptive statistics function. Within parentheses, we need to mention our variables. Here in my case, I have only two variables, that is height and yield. So I will mention ht, yld. If you have more than two variables or two observations, you have to mention them here. So use comma one after another. Put comma after mentioning last variable. Then we need to justify our stats. I will justify that for mean. So mention mean within double inverted commas. Again, I will explain. Here what I have done is I have taken my dataset, that is MMET, and I have piped it through in order to group our environments and genotypes. After that, I have piped it through in order to get the descriptive statistics. Here I have mentioned the descriptive statistics as height and yield, and I want here mean. If we execute, our output will be stored in MGE. Execute the object MGE in order to know the values directly in the console. In order to see the table, use view function. Within the parentheses, mention the object name, that is MGE. By using the values in this table, we can prepare our two-way table. Here you can see this is the average height of the genotype 1 is here. This is the average yield of genotype 1. This is the average height of genotype 2. This is the average of genotype 2 for yield. So we can use this value like this. We can use this value for preparing the two-way table for the variable height. I hope you guys get what I am talking here. So let me go back to the script and start coding for the next part. Here I will show you how to plot the performance for different variables using either heat map or line graph. So let me start with the variable height. I will store the first plot in an object known as PHD, that is performance of height. Here I will use GE underscore plots function in order to plot the heat map. Here within the parentheses, we need to justify our dataset, that is MMET. After that, we need to justify our environments. Then we need to justify the genotypes. After that, we need to justify the variable. Here, height, ht. You can see the variables are there in our data frame. Here you can see this is ht height, this is yield, YLD. Let me close other tables to keep the stuff clean. If I execute this line, the plot will be stored in an object known as pht. So in order to get the plot, execute pht. Here you can see this is the heat map. If I haven't taken the genotypes and environments with the factors as unique levels, then you wouldn't find this sequence, that is G1, G2, G3, G4. Instead, you would find G1, G11, G12, G2, G3. You can export the graph from here, but I will show it later. In order to get the line graph, what we need to do additionally is just to pass an additional argument known as type, which by default set to 1. If we change it to 2, we will get line graph. I will store the plot in an object known as pht2. Again, I will use the same function GE plot. Within that, I will mention the dataset name, that is MMET. I will justify environment, genotype, then the same variable height. After that, I will change the type to 2. In order to get the line graph, execute pht2. Then you will find this graph. This is the line graph. As you can see, the genotypes are ordered correctly. In the same way, we can use this function to get the heat map and line graph for the yield also. So here the same story continues. I will store the performance of yield in an object known as PYD and use the same function, that is GE plots. And within that, I will mention my dataset, environment, genotype, and the variable, that is yield here. If we execute this line, the object will be stored in PYD. So if we execute that object, then we will get the heat map. I will store the second type of graph in PYD2. Here the function goes similar to the function what we did for the line graph of height. Instead of height, I will use yield and change the type to 2. So if we execute PYD2, then I will get the line graph. So in the next step, I will show how to find the top variety or the winner variety with respect to the variable, that is height and yield. So let me get some space. So I will store the winners in an object known as win. And the function I am going to use here is GE underscore winners. Within that, we need to mention our data frame name, that is MMET. Then we need to specify our environments. Then we need to specify our genotypes. Then we need to select our variables. Here I will select the variables with respect to everything. That means all the variables. If you want a particular variable, instead of writing that line respect is equals to everything, you can use the variable straightforward, that is ht or YLD. If we execute this line, it will be stored in an object known as win. So I will directly view the table stored in the object win. These are the top performing genotypes. In the environment one, in terms of height, G6 is the winner. So you can consider these genotypes in case you think the higher value is better. If you think lower is better, you need to check for the ranks in reverse order. So let's find the rank of genotypes based on the value stored in the variables, either height or yield. Here I will store the ranks in the object known as ranks. The function is same, GE underscore winners. Within that, we need to mention all the same arguments what we passed in previous function. With that, we have to use an additional argument type. In that, we need to specify ranks in double inverted commas. So execute this line. After, I will directly view the table present in ranks. So this is the ranks table. Here you can see G6 is having first rank in terms of height in first environment. G10 second rank in terms of height in first environment. Same in terms of yield also. Here G1, G12, G3 have first, second and third rank in terms of yield in first environment. And in second environment, G10, G11, G12 have top 3 rank in terms of height. And in terms of yield, you can see here. And for the third environment, like this only you can follow. And you can also get more information about performance. In order to get that, you can use GA underscore details function. Within that, pass the same arguments which I have passed in the above functions. Keeping all these things aside, let's move on to the things which really matters more for us. As I said in the beginning, today I am going to use only fixed effect models. After taking your feedback, I am going to make another video on mixed effect models. So don't forget to give the feedback in the comment section. So let's start the analysis, beginning from the individual ANOVA. Here I will store all the output what I get from individual ANOVAs in this object. It basically refers to same only individual ANOVA. Why? Because here I am going to use only one line of code to get individual ANOVA of all the variables. Later I will show you how to dig into the different variables and get the ANOVA table. The function to calculate individual ANOVA is ANOVA underscore IND, which refers to individual only. Here in the yellow box, just above the individual ANOVA function, you will find the suggestion that what we need to key in for this function. So here we need to key in our dataset name, that is MMET, which refers to Maze Multi-Environmental Trials. Then we need to justify our environments, then our genotypes. After that, our replications. Here I will justify my variables in this fashion. So if you want to calculate ANOVA for particular variable, instead of this argument, you can specify the particular variable such as height or yield, here HT or YLD. So if you want a set of particular variables, after C within parentheses, we need to mention those variables. For those people who are looking for alpha lattice design, after this argument, we need to specify the blocks. If we execute this line, it will take some time to calculate the individual ANOVA. Don't worry, both yield and height variables are extracted, but here it's showing only yield. So let me show you how to get the individual ANOVA for the variable height. So from the object where our all individual ANOVAs are stored, if we select, that is if we use dollar symbol, we will get the parameters or the variables extracted. So from here we can select either height or yield. So from that, if we select, there is only one table, that is in the name of individual. So select the table and execute this line to get the individual ANOVA for height. So we will save this table in an object known as IAHT, which means individual ANOVA of height. So I will just copy and paste the command which takes us to the individual ANOVA table of height here. So if we execute this line, the table will be stored in IAHT. We can use the view function to view the table. So within view function, inside the parenthesis, mention the object name, that is IAHT, and execute to see the table in a new tab in the RStudio itself. In case you won't understand what are the short forms in the table headings, you can use the help. So in order to get help, type question mark. After question mark, we need to mention function name, that is ANOVA underscore IND here. So if you execute this line, you will find the help here. You can see the function is table, and you can find the usage, that is how to give the arguments here. Then just below the usage, you will find the arguments, what they are and how to use them. So in case you are using alpha lattice design, you can get the short forms here. For us, that is RCBD, we'll find the short forms here. So in the same way, we can use help for other functions also. So the most important thing here, which I think is, that is the examples. If we copy this example and paste it in the console and execute, still we will get the output because the dataset is built in this package only. So use this examples to track the new changes, because sometimes if we use the way which I have showed in this video might be wrong, because the function might be updated in the new version. So track the changes here. So I hope you guys will follow. Here I will show you how to do the Bartlett test across the environments for checking homogeneity of variances. There is a built-in function within the R itself that is known as Bartlett.test. Be careful with the spellings. Here we need to select this function. Within that we need to select our variable. So from the data frame MMET, we have to select the variable height. Then we need to relate it with our environment. So from the data frame MMET, select environments. After that, we need to justify our data, that is MMET, our data frame name. If we execute this line, then in the console, we will find the chi-square value or the k-square value here, and the p-values what we need. So in the same way, we can do all these steps for the next variable, that is yield. So from the object where our individual ANOVAs are stored, I will select the parameter or the variable yield. Within that, I will select my data frame, that is individual ANOVA. So if we execute, you can find the ANOVA just in the console, but in order to view it, I will store it in a separate object known as IAYD, individual ANOVA for yield. So just copy this function and paste here and execute. The individual ANOVA table will be stored in IAYD. So within the view function, if you specify the object that is IAYD, you can view the table in a separate tab. So for those people who are watching the video starting from the ANOVA, you can save the table by using a function known as write underscore XLSX. Within that, we need to mention the object where our table has been stored, and after that we need to specify the table name. Here I will specify the table name as yield A and B, that means yield ANOVA dot XLSX, that is the format for Excel sheet. If we execute this line, the table will be there in our working directory. So if you execute this line, the table will be there in our working directory and we can go there and check our table. So this is the cleanest form of individual ANOVA table. So with these values, you can prepare the traditional ANOVA, what we can see in case of other softwares. So after individual ANOVAs, we will get into pooled ANOVA. You can call it as joint ANOVA also. So for pooled ANOVA, I will address one variable after another. So let's work out for the pooled analysis of variance for the variable height. So I will store the pooled analysis of variance in this object known as PANV1, which stands for pooled ANOVA for the first variable height. So the function which I am going to use here is ANOVA underscore joint. So in the yellow box, as I said, for individual ANOVA, we will get the suggestion and we need to pass the argument as same as we passed in individual ANOVA also. So justify the dataset, environment, genotype, replication. So here I am selecting only one variable, that is height. So those people who are having alpha lattice design, you need to specify the block as seen in the suggestion box. So if we execute this line, we will get the pooled ANOVA in the console directly. So let me get this table out. I will store this table in an object known as PAVT1. It's the first pooled ANOVA table 1. So select the object where our ANOVA table has been stored and select the parameter height. So from that we can select these things, but I will select ANOVA, and if we execute this line, the ANOVA table will be there in the object known as PAVT1. So with the use of view function, you can view the pooled ANOVA table directly. So for the pooled ANOVA table for the yield, we have to follow the same procedures and the steps what we did for the variable height. So I will store the ANOVA table for yield in an object known as PANV2, which refers to pooled ANOVA 2. And I will use the same function ANOVA underscore joint. Within that, we need to mention same arguments, that is dataset, environment, genotype, replication, and the variable here is yield. So if we execute this line, we will get the ANOVA table directly, and I will store that ANOVA table separately in a object known as PAVT2, that is pooled ANOVA table 2. If we execute this line, the ANOVA table will be stored in the object PAVT2. We can use the view function to view the pooled ANOVA table of the parameter 2, that is yield. We can take this table out into Excel sheet by using the function write underscore XLSX, as I told in the case of individual ANOVA. So with that, let me get into the core part of this video tutorial, that is stability analysis. So let's start this analysis from ANOVA based stability models. So from here onwards, whenever an object ends with number 1, it is related to variable height. Whenever the object ends with the number 2, then it is related to the variable yield. So let's start with the environmental index. I will store it in an object known as ANN1. So here the function which is used is known as AMMI Kiraku. So sorry with the pronunciation, it is Italian. So if anything wrong, please do suggest what is the correct pronunciation. Within that, we need to mention our data frame name, that is MMET. Then we need to specify the environments, then the genotypes, then replication. After that, we need to mention the variable, here the height. Here the output will be stored in the object ANN1. So just print the object ANN1 to see what are all stored in that object. When we execute this line, the output will be there in the console. So these are the environmental indexes, and these are not applicable because there is only one unfavorable environment. Because of that reason, they are not applicable. In case if you have two environments, unfavorable environments, then you will see those values too. And we can view a particular object stored in the object ANN1. So within parentheses, mention the object name ANN1 and use $symbol and select the variable height only. So from that you can select all this table. I will select environment. If we execute, we'll find the table. So in the same way, we need to do the same steps for the variable yield also. So I will store the output in an object known as ANN2, and we have to use the same function, that is ANIKRECO. Within the parentheses, we need to pass on the same arguments which we passed above. Instead of height, we have to change the variable to yield. And if we execute this line, the object will be there in ANN2. In order to get a brief outlook, just print the ANN2, and in order to view the table within view function, select the object ANN2 and select the variable yield and select any table what you want. The next concept is Rick's equivalence. I will store the equivalence values of variable height in an object known as eco1. And the function which I am going to use here is known as equivalence. Within the parentheses, we need to mention the same arguments, the dataset name, environment, genotype, replication, and the variable here height. We can find our values just by executing the object where the equivalence has been stored. So these are the values which we need, the equivalence and equivalence percentage. If you have more number of genotypes, then we can access the table stored in the object eco1. Then we can view them. Just a second, I will take out all the unnecessary tables from the shelf. With that, let's find the equivalence values for the variable yield. I will store them in an object known as eco2. Here also the same function equivalence. Then within that we need to justify our dataset, that is MMET, environment, genotypes, replication, and the variable here is yield. If we execute, we will find the result stored in eco2. Then you can see what's inside the eco2 just by executing the object. Then we will find the values here itself. Alternatively, you can get the values also by printing the object. And the next concept is Shukla's stability variance. I will store the stability variance of the variable height in the name of shu1. Then the function which I am going to use here is Shukla. It starts with capital S. Then within the parentheses, we need to pass on the same arguments, dataset name, environment, genotype, replication, and the variable height. So if we execute this line, the result will be there in shu1. So just execute the object shu1 to get the results. In the same way, I will calculate the stability variance for yield also. Same function, same arguments. Only we need to change the variable to yield. Then you can find the results stored in shu2. In the same way, what I have showed in the above examples, you can find the tables stored in the shu1 or shu2 just by using $sign after the object name. So after this, let's get into the regression based models. So I will store the regression based model on the variable height as reg1. In order to get the model, I will use the function known as GE_reg. So within the function, we need to specify the data frame name for environments, genotypes, and replication. After that, we need to justify the variable. Here I will justify it as height. So if we execute this line, the output will be stored in reg1. So just print reg1 in order to see what are all the things stored in the output reg1. So the next most important thing is getting the ANOVA table based on regression models. So I will store the regression based ANOVA for the variable height in this object known as reg1 ANV, which refers to regression 1 ANOVA. So from the model where we have stored the first regression model, reg1, we can select the parameter or the variable height. Then in that, if we select, we can find these many tables. So from here I will select ANOVA. So if we execute, the table will be stored in reg1 ANV. So just view the reg1 ANV in order to find the regression based ANOVA for the variable height. For those who are watching the video somewhere from the middle, we can also take this table into the Excel sheet. In order to do that, we need to use write_exlsx function. Within that, we need to mention the object where our table has been stored. Here it is reg1 ANV. After that, the second argument should be the name. So within double inverted comma, mention the name and its format, that is .xlsx. So if we execute this line, the table will be stored directly in our working directory. So from the working directory, we can access the table in Excel format. So this is the table, as you can see, where the regression based ANOVA for the height variable has been stored. Let me close it. So I will go back to the code and show you how to plot this model. So in order to plot, use plot function. Within parentheses, just mention the model name here, reg1. So if you execute this line, you will get this graph. You can customize this graph. I will talk about customization later in biplots. In the same way, we need to follow the same steps for the regression model too, where the variable will be healed. Here I will store the regression model 2 in an object known as reg2, and the function will be same GE underscore reg, and we have to justify our dataset, environments, genotype, replication, and the variable here is healed. So the output will be stored in reg2. You can just print it in order to get a brief outlook. So I will store the second regression based ANOVA on the variable healed in this object. So from the model reg2, I will select the variable that is healed, and then I will select the ANOVA table. So if you select the regression table, you will get the values for regression coefficients and etc. in that table. So you can select that table also, and you can view the table which is stored in the object. Then you can plot the model. So within the plot function, mention the model name, that is reg2, and execute in order to get the graph. So after regression based models, let's get into non-parametric part of the stability analysis. And the first part of that is the superiority concept proposed by Linn and Bins. Simply, I will store the superiority index based on the variable height in an object known as super1. So the function which is used here is known as superiority. Within that, we need to just mention our dataset name, that is MMET, and our environments, genotypes. After that, we need to justify the variable. Here it is height. So if we execute this line, the output will be stored in super1. You can print the object in order to see what are all the things which are stored in super1. So in case if you won't understand what are all these table headings here, you can use the help function. In order to do that, just type question mark. After that, type the function name, that is superiority. If you execute, the help will appear here. So at the end, you can find the research paper based on superiority here by the original author. So you can read that paper in order to get more idea about the concept superiority, and this is same for other concepts too. So with the help of view function, we can find the table stored in the object super1. Here I will select the index table, and this you can do for the environments too. In the same way, I do calculate the superiority index for the variable yield. So I will store them in an object known as super2. Here also the function will be same, that is superiority. Within that, we need to mention the same dataset name, environment, genotypes, and here the variable will change to yield. So if we execute, it will be stored in super2. Then we can find a particular table within the stored object, and you can view them using view function. In the same way I did in the case of superiority 1, where the variability used was height. So the next concept is Fox top third criteria. If you don't know anything about this concept, use the help function. So question mark, after that question mark, type Fox. Here F starts with capital F, since that is a function name and that is based on the name of the author. So in the help, you can find the research paper, study that paper in order to get more information. So here also everything remains same, but the change is the function. So instead of superiority, we need to use Fox function, which starts from capital F, as I said. So within the function, we need to justify our dataset and environments, genotypes. Then the variable here, height, will be used. Then we can see what are all stored inside the Fox one. So use view function and get the table. In the same way, we need to do the same procedures for the variable yield also. So I will store it in Fox2 and use the same function, that is Fox. Within that, we need to justify our dataset, environment, genotypes, and the variable here is yield. And in the same way, we can view the table which is present in the Fox2 object also. So let's move on to the next concept, that is factor based stability analysis. So here the function what we are going to use is GE underscore factorial. Factorial refers to factor analysis. So let's store the output for the variable height in an object known as fact1. So function which I'm going to use here is GE underscore factor. Within that we need to justify our dataset, environments, genotypes along with the replication. Next we need to justify the variable. Here it is for height. So if we execute this line, yeah, in the console you can see there is a warning indicating that there are only one factors have been extracted. So we can't plot a graph because we need at least two factors as a coordinates in order to plot the graph. So we can find what are all the objects stored in the fact1 object by printing fact1. Here you can see there is only one factor. There are no other factor other than fa1. I just ignore the plot here. I will go back to the next variable, that is yield, and I will store the output in an object known as fact2. Then same function, same arguments, except the variable height. Here we will use yield. So if we execute this line, you can see there are no warnings in the console. That means we can plot the graph. So we can print the object fact2 in order to get a brief outlook at what are all the things stored in fact2. So here you can see there are more than one factors, that is fa1 and fa2 are here. So we can plot it by taking them as two different coordinates. So in order to plot the graph, just use plot function. Within that, mention the object name, that is fact2. So if you execute this line, you will get the graph. So if you don't know how to interpret this graph, just refer the supplementary information which I showed in the beginning of this video, or use help function to find the reference material for this. So we can use view function to find what are all the tables stored in the object fact2. Here you can find so many tables. Here the important table is the environment table, where the environment stratification has been stored. But here I will select principal component axis. So here you can find the PCA. So if you are interested more about this concept, you can ask for the help in the RStudio itself. So we can summarize all the stability parameters by using only one function, that is wrapper function. So this is like the summary of all our stability analysis. So let's get into that. So I will wrap all the stability parameters based on the variable height in this object, which refers to stability parameter 1, where the 1 is the variable height. So the function which I'm going to use here is GE underscore stats. So within that we need to mention our data frame name, that is MMET, our environments, genotype, replication, and the variable height. So if we execute this line, the parameters will be stored in the object stability parameters 1. So we can also dig for more information by using get model data function, and I will store those information in data 1. So with that, we view what are all the parameters that we have got from using get model data function simply by viewing the object data 1. With that, we can also view the main table which is stored in the object stability parameter 1. So these are the stability parameters. By using getModelData function, we can also find the ranks based on the different stability parameters. Here I will store my ranks based on the stability parameters with respect to the variable height in an object known as ranks p1. So here we need to use the getModelData function. Within that, we need to specify the object where our stability parameters are stored, that is stab p1. After that, we need to pass an additional argument known as ranks within double inverted commas. So if we execute this line, we will find our ranks stored in ranks p1. So you can see the table stored in the object ranks p1 with the help of view function. So these are our ranks. We can also follow the same set of procedure for the variable yield also. Here I will store the stability parameters based on the variable yield in an object known as star p2, which refers to stability parameters 2, and the same function g underscore stars. Again, we need to specify our dataset MMET, then the environments, genotypes, replication, followed by our variable that is yield. So here I will directly view the table which is stored in the stability parameters 2. Then in data 2, I will store my model data by using get model data function. Within that, we need to specify our object where the stability parameters has been stored, that is stab p2, and we can also view the table by using view function. So let me take out some tables from here. So I will store my ranks in an object known as ranks2 and use the same function get model data. Within that I will mention, so within that I will specify the object in which the stability parameters for the yield has been stored and pass additional argument ranks within double inverted commas. So we can view the ranks by using view function and get the information here. So at last, if you have any doubts regarding the table headings in the wrapper function, you can also use the help which is built in R. So after question mark, mention the function name, that is GE underscore stats. You will get the help here, so you can view whatever you want from this tab. As I said earlier, the metan is a complete package. We can use the functions which are built in this package in order to find the correlation between different stability parameters. So let's get into that. I will store the correlations between the stability parameters of the variable height in an object known as CSI1, which refers to correlation of stability indexes of the first variable height. So here the function I am going to use is core underscore stab underscore ind. Within that, we need to just mention the object where our stability parameters are stored. Here for height, it is stability parameters 1. So if we execute this line, the output will be there in CSI1. So if you execute the object CSI1, then we will get the table in the console, then the graph in this pane. So if you see the graph by zooming it, you won't see anything. So in order to get the correlation coefficient, we have to find the table which is stored in CSI1. So with the view function, find the table and view it in a separate tab. And in the same way, we can also find and view the p-values of the correlations. In the same way, following same procedures, we can get the correlations for the stability parameters which are related to heat. So here, only one thing I am going to change is, here I am not going to consider all the stats. Here I will consider only AMMI based stats. So within double inverted commas, mention AMMI and execute this line. And you can follow same procedure what I did in the previous step in order to find the correlation table and also the p-values table. Here you can see this is the heat map. So we can use this heat map very much. So in order to find what are all the arguments we can pass for stats, just ask for the help within the R itself and we can find the information here. And we can also find the tables which are stored in CSI2. So with all that said, let's move on to the most anticipated part of this video, that is AMMI model or AMMI model, whatsoever based on your actions. So I will call it as AMMI model. So let's deal with the first variable, that is height. So here I will store the model in an object known as AMod1, which refers to AMMI model 1. So the function which we have to use here is performs underscore AMMI. So within the parentheses, we need to mention our data frame name, that is MMET, our environments, after that our genotypes, then replication, at last the variable, it is height. In case if you are using alpha lattice design, then we need to specify the blocks also. When we execute this line, immediately after the execution, we will get the ANOVA table in the console and we can print the object in order to see what are all the things present in the object AMod1. And we can also plot the model in order to get the quantile plots and other things. In order to view a particular table, within the view function, select the object, that is AMod1, and in that select the variable, that is height. Then in that we can find these many tables. So I will select ANOVA. So if we execute this line, we will find the ANOVA table here. And we can also export this table or import this table by the help of write XLS function. So within that, mention the command which take us to the ANOVA table. Here the table is stored in the object AMod1. Within the variable height, you will find the ANOVA table. Next, we need to mention the name within double inverted commas along with the format, that is dot xlsx. So if we execute this line, the table will be there in the working directory. You can visit the working directory, and from there you can find the ANOVA in the Excel sheet itself. So let's get back into the RStudio and start fitting the model for the variable yield. So the same procedure, same steps will also follow here for yield. So I will fit the model in an object known as AMO2, AMMI Model 2. Here the function is same, performs underscore AMMI. Within that we need to mention our data frame name, that is MMET, and justify our environment, genotypes, replication, and the variable here yield. So when we execute this line, we will get the output, that is ANOVA, in the console directly, and we can also print and see what are all the things which are there in the object AMO2. We can also view that ANOVA table by selecting the objects which are stored inside the object AMO2. And we can also use the getModelData function in order to find a specific thing. Here I will get the significance value of IPCA. IPCA means interactive PCA. Within the getModelData function, I will mention my model name, that is AMOD1, that is ANOVA model 1, where the height is stored. And for the second argument, I will pass on IPCA p values in short form within double inverted commas. And in the console, you can see the output. And in the same way, we can also apply this function for the second variable, yield. So with that, let's move on to the biplots based on AMMI model. Here I will tell a lot about customization of these plots. In case if you are only interested to get these plots, you can get that by using plot score function. Within that, we just need to mention the model, either first model or second model, then the type, which will be is equals to 1, 2 or 4. So let's begin with the variable height. In order to access the plot very much easily and directly, I will store it in an object known as A1. The function we need to use here is plot scores. Within that, we need to mention the model, that is AMMI model 1, and the type will be 1 by default, so there is no need to mention. If we execute this line, the output will be there in A1. Just execute A1 in order to get the plot. Here you can see it is a plot between height and principal component 1. So in order to change the label height, we can pass the argument like this. Keeping all the things same, we just want to add an additional argument in the name, that is x.lab, which refers to x-axis label. So within double inverted commas, we have to mention the name. Here it is height. So if we execute this line, the output or the plot will be there in the object A1. So we can access the plot directly by executing A1. So here you can see the short form HT has been changed into height. So I will store the second plot, that is between principal component 1 and principal component 2, in an object known as B1. And the function which we are going to use is same, that is plot scores. So within that, we need to mention the AMMI model. Here for height it is AMMI model 1, and next we need to pass the additional argument, that is type, which is equals to 2. So after execution, the object will be there in B1. So execute B1 in order to get the second type of biplot. So here you can see this is the biplot, which is between principal component 1 and principal component 2. In order to get a polygon joining all the genotypes, we need to pass an additional argument. So in the B1 object only, I will use the same function, that is plot scores. Within that, I will mention the model and the type. So here I will pass an additional argument known as polygon, which is equals to true. So if we execute this line, the old biplot will be replaced by the new biplot with the polygons in the object B1. So execute B1 in order to get the plot with polygons. So the next step, let's see how to change the aesthetics of the biplot. So here also everything remains same, but here I will start the code in the second line, since it will be easy for you to look at the code. So after the first argument, we need to end it by comma only before getting into the second line also. So here in the second line, I will mention a type which is equals to 2. So after comma, we need to enter into the next line. So here I will change the color of the environments. So mention the color within double inverted commas, that is blue. Here I want to highlight only specific genotypes. So first I will set all the genotypes into transparent color. Later I will highlight the specific genotypes. So in the next step, I will change the color of the line which is connecting the different environments into orange. So I will highlight the first two genotypes, that is G1 and G2. So here I am mentioning two genotypes. In order to do that, we need to use C. After that, we need to open parenthesis. So within parenthesis, mention the genotypes, that is G1 and G2. Or if you want to mention other, mention within double inverted commas. So between each genotypes, we need to mention commas. Okay. So in the next argument, I will pass on the color which has to be used in highlighting the two genotypes. That is dark cyan. So mention the color name within double inverted commas. And this color has to be compatible with R. So don't mention any other colors if you don't have any idea about them. At last, I will also expand the axis. So if we execute this line, the object will be there in B1. So execute B1 in order to find the plot. So this is what my customization looks like. So you can do your own customization. And I wanted to talk about how to handle overlapping. For that reason, I am going to plot this graph and show you how to handle them in different ways. So I will also show you how to export the graph into the working directory. So here I will store the graph in an object known as C1. So use plot score function. Within that, mention the model. Here for height, I am mentioning AMMI Model 1. Then the type of graph. So here it is fourth type. So if we execute this line, the graph will be stored in C1. So if we execute C1, we will see the graph in the plots pane of the RStudio. Here you can also find there is a warning indicating that there are 6 unlabeled points. So those 6 unlabeled points are there when we are viewing the graph within the RStudio in the plots pane. If we zoom in, you can find here all the labels are there. That means 11 labels are there. Only one label is missing. In order to get that one label, we have to export this graph with optimum amount of resolution. Here, in order to get other 6 labels, I will logically double the width of the graph. So it will automatically increases the height if the aspect ratio has been maintained. So if we save here, the graph will be stored in the working directory. So after saving, we will get a preview here itself. Here you can see all the 12 labels are being present in this graph. So this is what the hack we need to do in order to handle the overlapping. So in order to find what are all the other things we need to do, you can ask for help. So after question mark, mention the function name, that is plot scores. So if we execute this, you will find the help here. You can use these many arguments. Here the most important one is repulsion. So here by altering the repulsion, you can avoid overlapping, and we can also address this issue by expanding the axis. Then we can also avoid them by decreasing the size of the different objects, whether it is environment or genotypes. So let's start the customization beginning from altering the repulsion. So if we alter the repulsion and then execute the plot, so after that also, if you are seeing there is overlapping means, then try decreasing the size of the labels. So here I will show you how to do that along with changing the axis title. So I will store the plot in the same object, that is C1, same function, that is plot scores. Within that we need to mention our model name. This is A mod 1, that means AMMI Model 1 because height. Then I will change the type to 4. In order to reduce the size, here it is of genotypes. So we need to select this argument size.text.genotypes. I will reduce it to 2. Then I will select the custom name for x-axis and y-axis. Then I will take out the name of this plot. So if we execute this line, the graph will be there in C1. Execute C1 in order to find our customized plot. Here you can see there are only 4 missing labels. So if we zoom in, all the 12 labels will appear here, and this is one way we can customize the plots. So here don't consider that E1 that has been there by mistake. So you can also address this issue by simply taking out all the labels. In order to do that, pass this additional argument and set it to 0. So if we execute this line, the new customized plot will be there in C1. So simply execute C1 in order to see the graph, and here you can see there are no labels. And we can also arrange all the biplots what we have got in AMMI model in a single row. That means side by side. So don't do this until unless you are having less number of genotypes. So if you have more number of genotypes, there will be so much overlapping and there will be so much warning. So all the steps what we done for the variable height will also repeat for the variable yield. So here the only change is the model which we mentioned within the plot score function. Here it will be AMMI model 2. So the output will be stored in A2. Execute A2 to get the first graph, and also you can change the short form YLD to yield. Here you can see the label has been changed to yield. In the same way, we can also get the second type of graph, and I will store it in the B2, and the function will be same plot scores. Within that we need to mention the second model, and the type will be equals to 2, and we also need the polygon connecting the genotypes. So execute B2 in order to get the graph, and in the same way we can also get the nominal yield plot. Here we need to customize the x-axis label and y-axis label. So within double inverted commas type the text which is desirable for you. So here also don't mention E1, it is environment only. Here I have done a small mistake, so pardon me with that. With that, let's move to AMMI based stability statistics. Here I will store the output in an object known as ABS1, which stands for AMMI based stability statistics for the variable 1, that is height. So the function here is AMMI underscore indexes. So don't mess with the case of letters. So here if you mention the model, that is for height AMMI model 1, and if we execute, the output will be there in ABS1. So if we print the object ABS1, then we will get a brief outlook at what are all the things which are stored. And we can also dig at a particular table by using view function. Within that we need to select the object, that is ABS1. After that we need to select the table which is present in that object. So like that we can find the table here. In the same way we need to follow the same steps and same procedure for the second variable. And here I will store the statistics in an object known as ABS2, that is AMMI based statistics for the second variable yield. So the function will be same AMMI underscore indexes. Within that we need to specify the model, here AMMI model 2, because that is the model which contains the variable yield. So if we execute, the statistics will be there in ABS2. So just print ABS2 in order to get the outlook, and we can also dig at a particular table which is present in the ABS2 like this. In case anyone is wondering about the type 3 biplot of AMMI models, so here is the answer. In order to get that, we need to understand and know about the different or a new concept, that is fitting an AMMI model based on weighted average absolute score. And the work on this concept is done by the author of this package itself. In case if you want to know how to interpret the third type of plot, refer the supplementary information which I showed in the beginning of this video. Here I will store the model in an object known as WAAS1 for the variable height. And here the function which is used is WAAS. Within that we need to pass the argument similarly what we passed for perform AMMI function, that is our dataset, environments, genotypes, replication. After that we need to specify the variable, here it is height. In case of alpha lattice design you need to specify the blocks also. If we execute this line, the output will be there in WAAS1. From that we can dig into a particular table by using view function, and we can also print the object WAAS1 in order to see what are all the things are present in WAAS1. So with the help of WAAS1 model, we can also get the type 3 plot here. In order to get that, I will store the plot in an object known as WP1 underscore 3. Here also the same function, that is plot scores. Within that we need to mention the model, here WAAS1, and the type of the plot which is equals to 3. Later execute the object in order to find the graph. So if you want to interpret this plot, check for the supplementary information as I said beginning of this concept. Remember, we can also get the other type of plots such as the graph between principal component 1 and 2 by using the WAAS model only. And in the same way we can also fit the WAAS based AMMI model for the variable yield also. Here I will store the model in an object known as WAAS2, and the function will be same, that is WAAS. Within that we need to justify our dataset, environment, genotype, replication, and the variable here it is yield. And in the same way we can also access a particular table which is stored in the object WAAS2, and we can also get the type 3 plot by using the model that is WAAS2 here with the help of the same function plot scores. And there is no need for us to fit the AMMI model once again in order to find the AMMI based statistics. Here also we can use the same function that is AMMI underscore indexes in order to find the AMMI based statistics for the first variable height. So within parentheses mention the model which is based on the variable height, that is WAAS1. So after execution we can find the table which is present in the object WAAS1, and we can also print in order to get a brief outlook. The same story will continue for the second variable yield also. Here the only change is within the AMMI indexes function we need to pass the model where the yield has been stored, here WAAS2. And in the same way we can also view the table which is present in the object WAAS2. And the most unique thing which I found in this package is we can also cross verify our AMMI model, but unfortunately I don't have more than two principal component access in order to go for cross verification, and the computer, as you can see, this is not up to date in order to do that. If you have a computer with the processor such as i7 or i5 or i9, in case you can proceed for the cross verification. And if your system is outdated like me, which is having only dual core Pentium processor, don't proceed further because you will stuck up there for more than 20-30 minutes, and that will be problem for you in continuing your analysis. So if you have good processor, do cross verification at the last part of your analysis. So the function which is used here is cv underscore ammif in order to verify full number of axes. So you can refer the supplementary information about cross verification. I will skip this part and jump into the part or last part or final concept, that is GGE models. And the most important part you need to know in this concept is the model options. So in brief, these are the model options which are available. In case if you want to know them in detail, refer the Ann and Tinker research paper which I showed in the earlier part of this video. Here, in order to get different kind of GGE biplots, we need to tweak around with the single value partition. By default, the single value partition will be set for the environment. So by default, we can get 4 different type of biplots. And by setting single value partition to genotype and by setting single value partition to symmetrical, we can get 3 biplots each. Totally 10 different biplots. So first we will get the model in which the single value partition is set to environment by default. So I will store the model in an object known as GGE underscore model 1. So here the 1 refers to the variable height, and the function which is used here is GGE. Within that we need to justify our dataset, environment, genotype, and the variable height. So if we execute this line, the output will be there in GGE model 1. So let me fix this. So simply we need to delete this. We can also predict the response variable based on principal components. To do that, we need to use predict function. Within that, we need to pass our model, that is GGE model 1. So if we execute, the results will be out directly in the console. So if you want to save these results, you can save it in a separate object. So I will save this in this object, and later you can view what are all the tables which are present in this object also. So same procedure, same steps will also be followed for the second variable here, yield. So I will store it in an object known as GGE model 2, and the function will be same, that is GGE. Within that we need to specify our dataset, environment, genotype. After that we need to change the variable from height to yield. So if we execute this line, the output will be there in GGE model 2, and we can do the same in order to predict the values, and we can save these predicted values in a separate object also. With that, let's move into the GGE biplots. Here the first biplot which I am going to show is a basic biplot. So first we will deal with the variable height here. So I will store the biplot in an object known as bbp1, that is basic biplot for the variable 1, that is height. So use plot function. Within that we need to pass our model here GGE model 1 because that is the model which is based on the variable height. So if we execute this line, the type 1 will be there by default. So in order to see the basic biplot, we need to execute BBP1. So if we execute this line, our first basic biplot appears here. So don't forget the customization that what we did for AMMI based biplots. So here I will change the color of the genotypes to red. So in order to do that, we need to pass an additional argument of the model and type here color dropgen. I will save it as red within double inverted commas. So if we execute, here you can see the biplot which is having genotypes in red color. And for the yield also, here everything remains same. The only change is the model. We need to use GGE model 2 because that is the model based on the variable yield. So execute basic biplot 2 in order to get the biplot based on the variable yield. So the next type of biplots is discriminativeness versus representativeness. First we will deal with the variable height. Here I will store the plot in an object known as dvr1, that is discriminative versus representativeness for the variable 1, that is height. So the function will remain same plot. Within that we need to pass the model here GGE model 1 because of variable height, and the type which is important. So we need to pass it as 4. Then we execute, the plot will be there in dvr1. So if we execute dvr1, then we will get the biplot describing the discriminativeness versus representativeness based on the variable height. For the yield also same story continues. Here I will store the plot in an object known as dvr2. Then here the function is plot only. Within that we need to change the model from GGE model 1 to GGE model 2. After that we need to specify the type of biplot which is here 4. Then if we execute, the plot will be there in dvr2. Then execute dvr2 in order to find the biplot. So one catch from here is, if you want to change the way the plots looks is, then we can change the theme. So in order to change, pass an additional argument justifying the theme. Here I will select theme gray. So here you can see the plot has been changed its theme and stored in dvr2. So when we execute dvr2, we will find a different looking plot. Then in order to know which are the different types of theme which are available in the ggplot2, you can use the help here. So the third type of plot will help in finding out the ranks of environments. So here first we will deal with the variable height as usual. Here I will store the ranking of environments based on the variable height in an object known as RE1, and the function will be same, that is plot. Within that we need to specify the model where the variable height has been used. Here that is GGE model 1. Then the type will be 6. So if we execute this line, the object will be there in RE1. So execute RE1 to get the plot depicting ranking of environments. And the same story continues for the yield also. Here I will store the plot in an object known as RE2, and the function will be same plot. Within that the model will change. Here GGE model 2 because of the variable yield. Then type which is equals to 6 only. So if we execute this line, and then if we execute RE2, then we will get the biplot depicting the ranking of environments based on the variable yield. And the next type of GGE biplot is relationship among environments. So let's see how the relationship among environments are there depending upon the variable height at the first. So here I will store the plot in an object known as RAE1, which means relationship among environments based on the variable 1, that is height only. Here the function will remain same, that is plot. Within that we need to mention the model which is based on the variable height. Here it is GGE model 1. Then the type of the plot here is 10. So if we execute this line, the object will be stored in RAE1. So execute RAE1 in order to get the biplot depicting the relationship among environments. So here you can see that. The same story will also continue for the yield also. Here I will store the biplot in an object known as RAE2, and the function is same, that is plot. Within that we need to specify the model based on the variable yield, that is GG model 2. then the type will remain as 10 only. So if we execute, the plot will be there in RAE2, then execute RAE2 in order to find the biplot based on the variable yield depicting the relationship among environments. In order to get the other three biplots, I will change the single value partition from environment to genotype. And I will store the model in an object known as GPG1. Here GPG refers to GGE model partition on genotype, which will be easy for me to remember. So I am giving the shortcut like this, and one refers to the variable height as usual. And in order to model within GGE function, we need to pass our dataset, environment, genotype, and the variable here is height. Then we need to pass the additional argument known as SVP, and we need to set that for genotype. So mention genotype within double inverted commas. So if we execute, the model will be stored in GPG1, and I will store the predicted values in this object. In order to do that, we need to use predict function. Within that, we need to mention the model. Here it is GPG1. So if we execute, the output will be there in the object. So you can view this object in order to get the table. So in the same way, we need to follow same procedures in order to model for the variable yield also. Here I will store the model in an object known as GPG2, and the function will remain same, that is GGE. Within that, we need to specify our dataset, environments, genotype, and here the variable is yield, and we need to set the single value partition to genotype. And in the same way, I will store the predicted values in a new object here for the variable yield, and we can also view those values in a separate tab as a table. So let's get back into the biplots. So here the biplot which I am going to show based on the model where the single value partition is set to genotype is mean performance versus stability. So let's start with the variable height. Here I will store my first biplot in an object known as MVS1, which refers to mean versus stability for the variable 1, that is height. Here also the function will be same, that is plot. Within that, we need to mention the model where the single value partition is set for the genotype, and here for the variable height is GPG1 and the type will be 2. If we execute, the plot will be there in MVS1. So execute MVS1 in order to see the biplot depicting mean performance versus stability based on the variable height. Here for the variable yield, everything will remain same. The only change is within the plot function, we need to specify the second model, that is GPG2. So if we execute this line, the output will be there in MVS2. So you can execute MVS2 in order to find the biplot depicting the mean performance versus stability based on the variable yield. And the next type of biplot is examining a particular genotype. So let's start with the variable height. So here I will examine the performance of genotype 6 for the variable height. So in short form, it refers same only, examining the genotype 6 for the variable height, that is EG660. So within plot function, mention the model GPG1 and the type of the plot here is 7. Then we need to pass an additional argument in order to select a particular genotype. Here we need to select the genotype within double inverted commas. So I will select G6, that is 6 genotype here. So if we execute this line, the plot will be stored in the object. So execute the object in order to get the biplot. In the same way, I will examine the genotype for the yield also. Here I will select the first genotype. So in short, EGY1. So examining the genotype 1 for yield. So open the plot function. Within that, mention the model which is based on the variable yield, that is GPG2, and the type will remain same only, that is 7. After that, we need to select the genotype. So mention G1 within double inverted commas. So execute this line and later execute the object where the biplot is stored. And the last kind of biplot by using models where the SVP is set to genotypes is ranking of genotypes. So here I will store my plot in an object known as RG1, that means ranking of genotypes based on the variable 1, that is height. So same function plot. Within that, we need to pass on the model based on the variable. Here it is 1 because of height. then the type will be equals to 8. So execute the object where the plot is stored in order to see the biplot. Ignore the warnings, they don't have any real effect on our analysis. So then after the variable height, let's get back into the variable yield. So here everything remains same. The only change will be within the plot function, we need to specify the model GPG2 because of the variable, here it is yield. Then the type will remain same, which is equals to 8. So if we execute this line, the output will be there in RG2. So execute RG2 in order to find the biplot indicating the ranking of genotypes based on yield. So finally we are in the last part of the video. Here we need to change the single value partition to symmetrical in order to obtain the other 3 biplots. So let's start the modeling from the variable height. So here I will store my model like this: GGE model partition symmetrically for the variable height, so 1. And the function which is used is GGE. Within that we need to justify our dataset, environments, genotype, and the variable here it is height. So after that we need to set the single value partition to symmetrical. So within double inverted commas mention symmetrical. So if we execute this line, the output will be there in GPS1, and we can use the model to predict the values, and later we can view that table also. In the same way, we need to develop the second table based on the symmetrical partition only for the variable yield. Here also I will save my model in an object known as GPS2. Here the function which is used is GGE. Within that we need to specify our dataset, environment, genotype, and here the variable which is used is yield. So with that we need to pass an additional argument, that is SVP. Here we need to set it for symmetrical, and we can also use the model to predict the scores. Sorry, instead of using predict I have used GGE, so I will replace GGE by predict. So if we execute now, the scores will be stored in PGPS2, and with the help of view function we can find the table which is stored in the object. And the most important biplot based on symmetrical partition is what won where or which won where. So let's look what won where based on the variable height. Here I will store my plot in an object known as W1, and the function which is used here is plot only. Within that we need to mention our model. Here for the height it is GPS1, and the type which is used here is 3. Then if we execute this line, the plot will be there in W1. So execute W1 in order to find the plot. So this is the biplot, which is very much important for us. So if you want to customize, use the same arguments what I have shown in AMMI Biplots, and they also work here. And the same procedure is followed for the variable yield also. Here I will save my biplot in an object known as W2, and the function is same plot. Within that mention the model. Here GPS2 because of the variable yield. Then the type will be 3 only. When we execute this line, the output will be there in W2. So execute W2 in order to find the which won where biplot based on the variable yield. So the next type of biplots helps us in evaluating a particular environment. So here I will consider the first environment for the variable height. So E1HD here refers to that only, and the function which is used here is plot. Within that mention the model, here GPS1 because of the variable height. After that we need to specify the type of the plot, which is equals to 5. Then we need to select the environment. So within double inverted comma mention the environment which is needed, that is E1. So if we execute this line, the object will be stored in E1HD. Then execute E1HD in order to get the plot. And in the same way I will examine the second environment for the variable yield. So here E2YD refers that only second environment for the variable yield. Then within plot function mention the model. Here the model will be GPS2 because of the variable yield. Then the type will be same, that is 5. Then we need to select the environment. Here I will select the environment E2 within double inverted commas. So execute this line and the output will be there in E2YD. Then execute E2YD in order to find the biplot. This is the last type of biplot in this video. So it will be useful in comparing two different genotypes. So let's start with the variable height. So let us compare the height between second and third genotype. Here the function will be same, that is plot. Within that we need to specify the model. Here for height it is GPS 1 and the type of plot is 9. After that we need to select the first genotype. So here it is 2 and we need to select the second genotype. So here it is 3. So we need to mention both of them in double inverted commas. So when we execute this line, the output will be there in the object. So execute the object in order to find the biplot. And in the same way, we can also compare the heat levels between two different genotypes. Here I will compare the heat level between the first genotype and the sixth genotype. So here YD1 and 6 refers same only. So within plot function, mention the model which is GPS2. Then after the type, it is 9 only. Then we need to select the first genotype. So here it is G1 and the second genotype here is G6. So mention both of them in double inverted commas. So after this, when we execute this line, the output will be there in YD1 and 6. So execute that object in order to find the biplot. So these are the 10 different kinds of biplots and we can toggle between them from pressing these buttons. So if you want to get the plot, you can take a screenshot by zooming in, or we can get a good biplot by exporting it as an image by increasing the resolution and maintaining the aspect ratio. So I have just doubled the resolution. If we click on save, the plot will be saved in the working directory. So here you can see, and I consider this is the most appropriate method for exporting a plot. So I hope you guys understand my efforts and like the video, subscribe the channel, because that is the only way you can support me. And if you think I am not good enough, so please do comment in the comment section whether you are able to follow me or not, or you can able to do the data analysis. In case if you are stuck up anywhere in the middle, I would like to send this soft script for you so that you can put the dataset and the script in a one folder. Then you can set that as working directory, then start executing each and every line so that what I have done here in the video will be repetitive in your computer. So in that case, please do attach your mail ID in the comment section. I will send the script and the dataset. At last, if you came up to here means, then you can also deal with the biometrical models and even mixed models also. Here I would like to show one of the important concepts, that is how to calculate genotypic, phenotypic and residual correlations. Most often we will calculate them by environment wise. So here let's take out the first environment into a separate table. Here I will store it in an object known as DE1. So with the help of subset function we can do that. So within parentheses mention the data frame, that is maze multi-environmental trails MET, and for environment select E1 within double inverted commas, and here we need to use double equals to sign. So that is how we will select. So with the help of view function we can find the table which is present in DE1, that is the data set of the first environment. So here you can see only the genotypes from the first environment are there. Here I will store my correlations and covariances in an object known as CRCV, and the function which is used to calculate the correlations based on the design is this. And within the function we need to justify our dataset. Here it is DE1, that is the dataset of the first environment, then our genotypes, then our replications, and we need to find it with respective to variables, here height and yield. Then we need to justify our design. Here it is RCBD. So within double inverted commas mention the design as RCBD. When we execute this line, all the correlations will be stored in CRCV. So when we execute CRCV, we will find our correlations directly in the console. Yes, if you want to view them as table, so within view function mention the object here CRCV. Within that, if you want to select a particular table, type dollar symbol, then all the tables which are present in that object will appear. So from here I will select the genotypic correlations. So you will get the correlations here. In case if you are finding any difficulties in finding a particular table, you can find all the tables from the environment tab. So just click on them, you will find the tables. So finally, thank you for your support. I have just got my custom URL so that you can share my channel with others. So in the playlist, you will find so many other videos based on the data analysis.